All right, what's up, guys? Chris the Ninja here, and welcome back to study sessions. I gotta turn my volume down because this is gonna be like blasting my eardrums. Yeah, we're back. We're back with control systems. Um, yeah, we're back with control systems. So if you remember last time, um, you remember from last time, we went over the basics of control systems. So just like a quick recap, we have our closed loop systems, which are these over here. They're more accurate, more reliable. There's a feedback loop, but they are more expensive, more complex, and harder to calculate. And you can have a proportional controller, a derivative proportional controller, or integral controller with proportional control. And this could be a PI, PID, PD, or just a P controller. So you mixing those three letters together. An open loop system, you don't have any feedback. They're lower cost and simple to build and calculate, but there's no feedback. They're not very accurate and not very reliable. Um, and so we worked with the motor and rod example that I learned in class. If you have the professor that I have permission from, shout out to you, Dr. Song. Appreciate you. Uh, he gave me permission to like do the notes, but not the homeworks. So this is why you won't see the homeworks done on here. Um, But yeah, we use a motor and rod example. This is the equations that you would need to calculate that, but this is just the derivation part. Quick little derivation of how velocity and position and acceleration are all related. And you have your proportional controller. So then you have how your output will go. It will start at 0. It will eventually approach 90. The error will start at 90 degrees off and eventually drop down to 0 or around 0. Um, there will always be there always will be an error. Um, and the errors can be calculated with the reference point minus the output. So, like as an example, let's say the reference is at 90 and the output's at 10. That may be like right about here. You now have the error at 80 degrees. If we have a slightly different output graph, wherever it crosses the line here, where it's crossing over the reference point that we're looking for, then you could have the error dropping below the point and then coming above the point and then dropping again. You want that to be lined up exactly where it lines up. And then you have proportional controller, and that lines up alongside that as well. Then we did our PID controller. One note about the PID controllers is that you can't mix signals and blocks together. So if it's a block like this might be a P, C, V, I don't know, whatever letter they decide to give you. You can't mix the blocks together. So you have to derive this signal and say like this is equal to this signal times all this, but then you have to derive what this signal is supposed to be. Um, and then that led us to welcome to the stream. Thanks for being here. Appreciate you tuning in. That led us to this equation right here, the shortcut for the Laplace domain. You have PC over 1 plus P times C. Um, and then as you can see here, you can see the graph output here. As it's changing, you see the error going below 0, above 0. The integral graph does not change below 0. Um, and yeah, so then we got into the Laplace transform. So we have the function on the left and the Laplace output on the right. So an impulse function just goes to 1, step function 1 over s, ramp function 1 over s squared, natural function, which is e to the minus at, that goes to 1 over s plus a. You have the natural times a ramp function, which is 1 over s plus a squared. You have a sine function, that's omega over s squared plus omega squared, cosine function, which is s over s squared plus omega squared, which is something I actually need to update for y'all. I forgot to write it last night, but it's fine. Um, Let me write that real quick. That's when you have this right here. So if you watched the last video and you were like, what the heck is that? My bad. Sorry. Then you have the natural time design function, which is e to the at or e to the minus at times sine omega t, which comes to omega over s plus a squared plus omega squared. Natural times cosine is the same thing, except now you have s plus a over s plus a squared plus omega squared. So that's just a quick recap. Then we had our properties. You had your linearity property, which is basically like it's just going to be a line. Like if it's a line, it's going to be a line anyway. Derivative, you have s times f of s. Integral, 1 over s times f of s. Time delay, you have negative s times lambda, where lambda can be found through the Laplace transform of f of t minus lambda. And then you have f of s plus a that breaks down to this, and you essentially just have this function here times f of s. And then we did a quick example. So we noticed that this is a time delay function right here. We pull that out, we set this equal to 0, we find that t equals 1. So when t equals 1, you multiply everything by 6. Um, so omega equals 6, and then your lambda equals 1 because it would be t minus lambda, and to get that equal to 0, or if them equal to each other, it would just be dividing by 6 gives you that 1 value. So I hope that all makes sense. So it should be this right here. So now moving into the more complicated things, we're going to move into um, obtaining the transfer functions. Let me see if that's actually on our midterm review. So you're trying to derive the transfer function from a block diagram. Trying to find a way to like actually do this real quick. Uh, so in this system, I can copy this one over real quick. My iPad can cooperate with me. Okay, so we want the transfer function of this. We want the transfer function of this right here. We have plus and minus. So the way we can get that is we want we want ys over RS. But what does that equal? Well, if you remember from last time, I told you that you can get YS over RS equals PC over 1 plus PC. Now, I'm not the greatest at algebra. I'll admit that. So me trying to derive it for you would probably just confuse you more. But essentially, you divide a bunch of stuff out, and it comes out to where you have PC equals 1 plus P, 1 PC over 1 plus PC. So we have P of S. If we have P of S right here, and we have CS over here, then we just need to multiply these two together and then do 1 plus that multiplied together. So our equation for Y over S, or YS over RS, is equal to A1 A1S over B1S plus B. That's multiplied by KP plus KI over S. And then we're dividing that by 1 plus A1S over B1S plus B times KP plus KI over S. So that's how we get that. Then you're going to distribute everything together. Um, so the way we can do that, because like I didn't really get a chance to do this slowly myself. So we're gonna pick our lovely diamond green. So we have A1S times KP, that's over B1S plus B. And then we're adding that to A1S KI over S times B1S plus B. Now we need to get common denominators to add them together. So we multiply um the top by B1S plus B. We multiply this side by S over S. Then that gives us A1 S squared KP plus A S A1 B1 S squared. KI um plus A1 S KI B, and then the bottom will just become basically um S squared B1 plus, hold up. I told you I was bad at algebra. I forgot the entire bottom half of the equation. This is S times that, and then this is all multiplied by 1 plus A1 S B1 S plus B KP plus KI over S. And this is multiplied by S. And then some algebra later that like some algebra later. You get this. This is the simplified version of the equation because you have the b's canceling and stuff like that. The b's cancel, some of the a's cancel. And this is what you end up having. So once you get to the transfer function part, actually let me see. Do I want to do that now or in a second? Um, okay, so that's basically how you obtain the transfer function from the from a system, but we can't really do anything with the transfer function when it's in the S domain. So we need to get it out of S domain. So we need to get back to time domain. The way we do that is the inverse Laplace. So we have inverse Laplace. So how does the inverse Laplace work? It's quite simple. Um, so to make things easier on me in terms of like how I'm going to teach this to y'all and how I'm going to study for this, I'm just going to use the same example, but I'm going to work through it for each step. So just as a quick note, so this is a side note, inverse Laplace is basically just like undoing the Laplace transform. So if we had, let's say, 5 over s, or we had 6 over s squared, or even if we had like square root of 2 over s plus 2, this would convert back into just 5. That would convert, yeah, back into 5. This would convert back into 6t, and this would just convert back into um sine of square root of 2 t, if that s was squared. So the inverse Laplace is not difficult to do. Inherently, the tricky part comes in with all the algebra and extra math steps that you have to take. So for our example, we will take also, in order to solve these problems, you have to be given the base function. Like you have to be given some form of the base function. It may not be what you want to see, but you need some form of the base function, or else you cannot solve the problem at all. So there we go. Let's work this one right here. So if we had our base function as a ramp function, so let's say this is our base. So our reference, not ramp, is it ramp? Step function. My bad. I meant step function. We have our base function as a step function. We have it as a step function. Then we know that the Laplace transform of the step function. Welcome to Train. Thanks for being here. Appreciate you tuning in. Is 1 over s. So we have so we need to have and this is rs. This is equal to rs. So in order to get the inverse Laplace of this, well, we now have y over s by itself, which means we multiply it over here by r of s. So if we have this times r of s, this is equal. We now have s squared plus 6s plus 8 over s squared plus 4s plus 3 times 1 over s. So the best way to go about this is to split the bottom portion of the function up into its roots. So we would then split this down. I'm gonna use red for this for the roots. So to break this up, this is another algebra problem. You have s times some s, that gives you s squared. You have 4s and you have 3. Well, what can you multiply together to get what can you add together to get 4 and multiply together to get 3? There's only one way you can do that, and that's to have s plus 1 and s plus 3. That's the only way you can multiply two numbers together to get 3 and add two numbers together to get 4. Only way you can do it. Then we're also multiplying by an extra s over here. And then the numerator will just be s squared plus 6s plus 8 still. So we will not be using this right this millisecond, but this is important to keep in mind and hold on to for a little bit later. So now we're gonna have to split the function again to find like how it adds up. So we'll have a C1. Oh, hold up. Um I'm gonna use like a nice coral green-ish color. Like a coral reef green. You got coral reef green for C1, C2, and C3. Because we have 3 roots, we have to have 3 constants. So we're adding these together. One will be divided by S, one will be divided by S plus 1, and one will be divided by S plus 3. And we're trying to find what is C1, C2, and C3. The easiest way to do this is to do the cover-up method. Um, so the way we do that is let's take the first one as S, right? So we're gonna take C1 over S plus C2 over S plus 1 and C3 over S plus 3. We're going to multiply all that by S. Well, multiplying by S, that gives us C1 plus C2 over S plus 1, or C2S over S plus 1 plus C3S over S plus 3. And then we're solving that for where S equals 0. Well, we now know that this will go to 0. This goes to 0. And now C1 is equal to this top function. So I'm just going to change color to purple. S squared plus 6S plus 8. Yeah, 6S. And then this is that times S? I think it's times S. Let me double check. So you multiply that by S. Yeah, you multiply this by S as well. But now that cancels out this S down here. So the S at the bottom just disappears. And we're still solving as if S equals 0. Oh, wow, we got 4 people in here. Welcome to the stream. Thanks for being here. Appreciate you tuning in. So now we just plug in 0 we plug in 0. So this is at we plug in 0 everywhere for where S is. We have 0 squared plus 6 times 0 plus 8 over 0 plus 1 times 0 plus 3. And that equals C1. So C1 ends up being, this goes to 0, this goes to 0. You have, this goes to 1, this goes to 3. 1 times 3 is 3. You have now C1 equals 8 over 3. Hope everybody's making sense out of this. So then you continue to do that for all of them. So going to number 2 now. We're doing C2. So now we can just fill in that this is 8 over 3. C2. Goodness, I gotta blow my nose. Hold on, y'all. I gotta grab a tissue real quick. Your boy can't breathe. I didn't drop that, by the way. I did not just drop that. I'm lying. Okay. So now let's just scroll down. We'll do C2. So C2. So if we're trying to find C2, we would have C1 over S plus C2 over S plus 1 plus C3 over S plus 3. We box that all in, and we're multiplying by S plus 1. And we're multiplying S plus 1 by the original function as well, the one that's boxed in blue. So this function up here is now being multiplied by the S plus 1 down here. But that makes it where this part and this part cancel. So that doesn't even matter. The end. It doesn't even get copyright claim. Doesn't get copyright claim because I'm not singing the rest of that song. Anyway, so now we have this S plus 1, this S plus 1 cancel. So just rearranging it so I can have everything where my brain makes it make sense. You now have C2 plus, geez, what do people want? Gosh, dang. Anyway, got C2 plus C1, S plus 1 over S, plus C3 of S plus 1 over S plus 3. Just want to make sure I did that right. Guaranteeing it. Okay, yes, I did that right. All right, and then that gets the good old box treatment, the good old box treatment. Put them in the box. Had to put the stick in the box. And we have S equal to -1 because if you solve S plus 1 equal to 0, you have to have S equal -1 in order for it to cancel out. So with S equals -1, this now goes to 0. This now goes to 0. So now you have C2 equals, and then once again, we're returning back to purple, S squared plus 6S plus 8 over S times S plus 3. And this is at S equals -1. Um, so plugging in -1, we now have -1 squared, -1 squared plus 6 times -1 plus 8 over -1 times -1 plus 3 equals C2. Oop, should use the same colors. Colors. Where's the colors? Okay. Anyway, um, and then that gives us 1 minus 6 plus 8. Minus 6 plus 8, that goes to 2. So 1 plus 2, that gives you 3. And then you have uh that gives you over 2 because this will be -1 times this goes to 2. -1 times 2 equals -2. So you have a -3/2 that equals C2. So scrolling back up, we can put -3/2 at the C2 value. And the final one is C3. So for C3, we would have C1 over S plus C2 over S plus 1 plus C3 over S plus 3. And then we have all this multiplied by S plus 3. That cancels with this. And now we have C3 plus C1 times S plus 3 over S plus 1 plus C2 times S plus 3 over S plus 1. And then that equals that equation again, S squared plus 6S plus 8 over S times S plus 1. And we're going to assume we already multiplied it by S plus 3 because the S plus 3 over S plus 3 would cancel to 1. Um, so now scrolling up just a little bit more. Now we're going to solve with S equal to S equals minus 3. So with S equals minus 3, you have C3. This goes to 0. This goes to 0. And then we're going to put the at. And then S squared. Oops. Goes to S squared. So that would be minus 3 squared. Minus 3 squared plus 6 times minus 3 plus 8. And then that is also minus 3 times minus 3 plus 1. So minus 3 squared, you get 9 plus 8, or 9 minus 18 plus 8. Over negative 3 plus 1 would give you negative 2 times negative 3 is now 6. And then the top simplifies down to negative 1 over 6. So then C3 equals negative 1/6. Dude, there's no way I actually like have this much space. Was it on the next part? I think I'm missing something, but I think the next step is to actually convert this back to the time domain. So now you have a 1/6 times, oh, let me scroll back up. Sorry about that, y'all. I have 1/6 times 1 over S plus, or negative 1/6 times 1 over S. Um, oh, goofy self. Silly me. Ah, no, silly me. I just bought a Korean 3 stories, that thing a trilogy. 8/3 times 1 over S plus, well, I guess it would be minus 3/2. Minus 3/2 times 1 over S plus 1 plus, or minus another 1/6 times 1 over S plus 3. So then converting this back using our I got it. Get the freak off the screen, Microsoft. You're cheesing up my live stream, bro. No, I'm kidding. Microsoft, y'all want to sponsor me? Hit me up. Um anyway, um so we know 1 over S, 1 over S comes from the step function. So that would just be like 8 over 3 minus um that would be minus e to the minus t, 3 minus 3/2 to the e minus t, because of that plus 1, and then minus 1/6 um e to the minus 3 t. And this would be the function of y t. I think, probably. I think that's right. Um, the last thing. So, by the way, the exam that we're covering, it might be different for y'all if y'all are farther ahead than we are. But the last thing we're going over with that part is the real roots, which is what I just solved for. And they're not repeated real roots, just regular real roots, distinct real roots, meaning that none are repeated. The last thing that we were told to take a look at was basically the final value theorem. So let me look and see how we're supposed to So the final value theorem, um, as you could probably guess and imply, if you think for 5.5 seconds or less, maybe you're super smart. Um, applies only if. So let me write this care. Let me write this to be very clear. Final value final value theorem only applies if the function yt or the output has a final value to reach. This means there's no I can't talk and write. I'm sorry, y'all. This means that no sine functions. Oh Jesus. This doesn't apply to a sine function, so does not apply. Sine or cosine functions, exponents, or exponential e to the xt, ramp functions, or anything else with an infinite reaching value. So that's something very important to know about the final value theorem. It has to have a final value. I could prove it like how it doesn't work without the final value, but I'm not about to do that. That's doing too much. Y'all got it, dogs. So let's say we have a control system that's like this. You get some input, goes to the control system, and it's 10 over 2s plus, I'll do 12. 12 over 2s plus 4. This is to avoid the confusion of, is that an S or a 5? And you have your output Y. So to get your time constant, you're going to need a time constant for this. You're going to need a time constant tau. With the time constant, the equation for that is B2 over B3. This is B2. This is B3. So now we have 2 over 4. So our time constant equals 1 over 2. Um, one important thing to note, one very important thing to note, do not, I repeat, do not do this. Don't do this. This is absolutely wrong. Don't do this. This is incorrect. The way you're supposed to do it, and we'll make this in our nice diamond green again. You need your value, you need your function multiplied by u of s. Okay? You need the u time u of s value multiplied by it. I didn't make the rules. I'm just telling y'all what not to do so you don't get a failing grade, all right? I'm just warning y'all. I'm warning y'all, all right? All right. We understand each other? Okay, cool. Appreciate you. Um, okay, so the u of s value in this case is 2 over s. So u of s is 2 over s. Because it's a step function, we're going to assume that this comes from a step function. We're going to assume that it's a step function that goes to that's where we get the 2 over s from. If it was a step function going to 3 or to 1 or whatever, it would be different. So then to convert this properly, we need to multiply we need to do the limit as y of s times that. We need to do the limit of y of s times s. So this is y of s. That would give us 12 over 2s plus 4. I need to scroll down. I'm sorry. 12 over 2s plus 4 multiplied by 2 over s times s. Well, this s and this s cancel, so we just have now 24 over 2s plus 4, and that's as That's as that happens. If we assume that S equals 0, so we say S equals 0, or if we set this to where S equals 0, not assume, that takes this out of the equation, this goes to 0. So now you have 24 over 4, and that gives us 6. So the final value of YT, it's also important to note that the time constant theorem, the way I found the time constant, it only applies to first order systems. Um, I just wanted to make sure that this other example was a valid example to work with. So we'll do one more. Welcome to the stream. Thanks for being here. Appreciate you tuning in. Just doing some good old fashioned studying. Oh, okay, here we go. That's where. So let's say we have this equation right here, or let's say we have this block diagram here. Now, what the cheese am I supposed to do here, man? You got all these heckin' variables and numbers and feedback loops, man. You gotta be flip flopping joking with me, dog. Come on now. No one can solve this. I can solve this because I'm Chris the Ninja. Also because my teacher is a really good teacher. Shout out to Dr. Song. Appreciate you. Okay. Um. So we just assign this as a C. You assign this as a P. We know that Y of S over R of S equals PC over 1 plus P over C, or one plus P times C. So then we got um 2 over S plus 2 times 3 over 1 plus 2 over S plus 2 times 3. Um Then we have to we pull the RS to the other side. What is RS? What did they did he give us RS? I don't think he gave us RS. Oh, I think R is three. Or the it's R is another step function, so R is another step function, so we need to multiply by R of S. So then that cancels with that, and then we end up having Y of S equals 6 over S plus 2 time over 1 plus 6 over S plus 2 multiplied by 3 over S, and that's our Y of S equation. Now to convert this back, like to get the final value theorem, we go back to our basics. Not really basics, but it's complex algebra that just simplifies down to what looks something kind of basic. We get our Y of S times S. That equals the we need the limit of Y of S times S, so we need a limit as t approaches infinity. So we'll have 6 over S plus 2, 1 plus 6 over S plus 2 times 3 over S times S. This S and this S cancel. At this point, we're getting to we're making where S equals 0. That's because the because of one of the properties of applies properly, I think. So now rewriting this, we now have 6 over 2 times 3, which would then give us 18 over 2, which is 9. So you have 9 over 1 plus 6 over 2. 6 over 2 is just 3. So you have now equals 9 over 4. So that's the steady that's the final value. However, there is an error. There is error associated with this. The error is offset by 3. You see this? The error is offset by 3. So now we do the steady state error to find the steady state error. So at steady state, we know the error is 3 starting. We know we're at 3 reference, where output is at 9 over 4, and this is error. If we multiply 3 by 4, you get 12 over 4 minus 9 over 4. That gives you 3/4, and that's our steady state error. So our steady state error that gives us 3/4. So after I have my long meeting for the night, I'm gonna be making my my university professor approved um information sheet. Appreciate you, Dr. Song. You're a real one, dog. That's just how he gives exams. Put some formulas and stuff on there. But I hope if you're taking this class either this semester or next semester that this helped you out a little bit. Um, This is everything that I know is going to be on the exam. Took me about 3 hours to study all this at the same time, but that's all I got for now. So with that all being said, I want to say thank you guys so much for watching this video in the stream. If you liked it, strike that like button like a ninja really would. Subscribe today to join the Shinobi, and I will see all you guys in the next one. I hope you have a great night.